Hello again. Hello again. Just before we continue your questions, I can't see any questions in chat. I can't hear any questions. So I make a short excuse. Is Samuel Travnicek present? It seems
Yes.
Yes, well, so your code has been the fastest.
Oh.
And you made a good job. My code is only 2 times faster than yours. That's a very good result. So now you have to choose the kind of wine. White, red, or pink?
I like red.
Red, okay. So once we will be able to meet, remember, tell me that I owe you a glass of good wine, and that's a red wine, okay? And I hope that we will be able to meet by the end of this term. The predictions we have made seem that in May there will be, let's say, 70% of people whose body has the experience, so they should be not vulnerable to the virus unless there is a big change. So I think that in May we will be able to meet and do something. Hopefully. So a good red wine. And after all, let's switch back to finite difference time domain, and I will try to describe what the problem with boundary conditions is. Now remember that we have an area and we have meshed it. Some values are discretized in delta x, 2 delta x, 3 delta x, and some are discretized half steps. So we have, for example, let's say we have a line where the h is discretized, then we discretize e. If this was a one-dimensional case, for example, so we would have to discretize ey and hx for a wave propagating in z direction. And if we try to calculate the green value, we have two neighbors, so we can calculate next time step for the green one. And if we try to calculate next time step for the red one, we have two neighborhood values. So we have the central difference for the red one. And this holds for all the points inside the mesh, but the mesh is not infinite. It would not fit into the computer, and even if it fitted, it would not be possible to elaborate so much nodes in a finite time. So we have somehow to restrict our mesh to a finite number of points. And from those points, a minority, but an important minority, lays on the boundary, which means that they have half step into the structure, a neighbor, but they are lacking a neighbor which is half step out of the material or out of the area, and therefore we can't update them using the ordinary formula. And that's the problem of boundaries. Finite difference time domain method is suited for working into closed volumes. But anyway, at the boundary, there is a problem. Now we have quite a good situation if the boundary is a metal or a good conductor, or let's say better, a perfect conductor. Because a perfect conductor, by definition, is a material which does not allow electric field into it, nor magnetic field. So we know that if there is a metal at the boundary and the next value is inside the metal, we could consider it's zero. So we are able to handle metallic boundaries, metallic enclosures quite well. This was the case, so I easily said we will somehow simulate a situation in a metallic cavity because it's quite simple with the boundaries. But what if we have, for example, a transmission line? Then it could be metallic, but at the ends we can't close it by a metallic layer because then it would not be a line, it would not be able to connect it to outside world in a meaningful way. So in this case we have a problem because the last layer of points has not enough neighbors to update. Of course this applies also to the other end, so even here there is a layer of values missing. So in this case we would have to find out another means how to update those values. And this means should somehow consider the physics behind. So in order to get a simple case, for example, what if this was a coaxial cable? We know a coaxial cable, it consists of a central conductor, which is mostly a solid metallic piece, and then there is the outer conductor, concentric, again metallic. So if we just restrain us to modes that do not propagate around the central conductor to the basic TEM mode, which propagates only along the conductor, then we would have a simple situation and we could approximate it by a 2D cut. So we just calculate a field on one radial half plane while the rest is symmetric. And in that case we would have more or less a 2D case again for solution. We will only solve the field in the dielectrics because we know that the metal shorts it. But anyway, there is some metal to remember. So this is the inner conductor and the out conductor. And we have a mesh over here, and it's quite easy to update those points inside because those electric values have neighbors half step shifted with magnetic field and vice versa. But at the end of the structure we have a problem. This is in fact the input of the line, this is the output of the line, and we have a problem there because if we just put there the same boundary condition as we did here, a metal, it would reflect. So it would not work. The first idea we could have, and that would work possibly with a piece of coaxial cable, is, okay, if we put there any boundary condition, like that consists of a single value, let's say, if we put there a Dirichlet or Neumann condition, it would not work very much. So what if we want to simulate this piece of coaxial cable, but in order to get no reflection here, we just extend the cable for several kilometers there and there, so that our simulation time would not be long enough to get a reflection from the distant end. So this is one of the possibilities how we can provide for a non-reflective condition at some place. We can extend the structure. Now, in a case of a 2D simulation, that might be attainable. So I just do not skip this possibility. Just imagine that in order to get this for a 3D structure, you have to increase the volume 1 million times. That would be a real problem. So, good solution, perfectly works. There is really no reflection because there is no end, no real end of the cable. But let's find something better. So can we have any better solution? Well, sometimes yes. For example, in the case in which we know the direction and velocity of propagation of the signal, we could supply another boundary condition which is perfect. Now, let's say that I have a set of cuts, so I have one cut for electric, another cut for electric field, another cut for electric field. Here I have the last cut for electric field, and there is a cut for magnetic field. And of course, I have the grid also partitioned in this way. So now what I'm missing is a set of values of magnetic field that is out of the structure and is a neighbor to the last regular cut of the electric field values. Now what if the cable was infinite and continued? Well, in that case, I would have this as a set of values, and well, in a real coaxial cable, we know two important things. First, the field of the dominant mode propagates along the cable with a known velocity of light, c, which for a lossless cable is C0 divided by a square root of the relative permittivity of the filling of the cable. So we have a very good guess for the velocity of propagation. And now it propagates along the cable, which means, in fact, that if I have a value over here, it travels along the cable. So if I know the value just here at some time, I know that it would propagate and at some time it will reach the other plane. So, for example, the same magnetic field travels to here a known time. If I set up the discretization in this direction so that in one time step the wave would just travel one space step, I know that I will have here the values that are here just one time step later. So, okay, in order to obtain those values, I can obtain them not using a finite difference time domain approach. I just say, okay, I would remember the values that have been in the last magnetic cut in the structure and put them here in one time step. Or if I decrease the time step, I have to always consider the ratio between the time step and the propagation through that time step, so that, for example, it is 2 time steps, 7 time steps, and I can just remember those values and use them as neighbors for the last cut after a certain number of time steps, most easily one time step. So now I can do a perfect condition for reflection. And really, if you program that, you will find out that the reflection from such a boundary is very small. Of course, numerical mathematics with numbers that are not represented to an infinite number of decimal places always produces some reflection. But you could easily get to a reflection of minus 120, even minus 150 dB, which means that the power reflected is 10 raised to 15 times lower than the power that comes to the boundary. And this is a precision at which we can forget about the reflection. So this is a way in which we can make a boundary that really does not reflect anything. I will discuss it a little bit for a coaxial cable. We have obtained a very good boundary condition that does not reflect anything based on the fact that we know the velocity of propagation, and this fact holds only for the dominant transverse electromagnetic mode. A coaxial cable, unfortunately, can host an infinite number of other modes, but they are propagating at lower speed, at least at lower group velocity. So we can use this boundary condition only if we have, for some reason, a good estimation that this field only contains the dominant mode. Now, why I'm talking about that? Well, because possibly you simulate a piece of coaxial cable not for fun. So if you have just a coaxial cable, a plain coaxial cable, you would not simulate it in a numerical way. You would just use an analytic solution, which is known, let's say, from 1926 by Shelkunov in Bell Labs Journal. So since then we have an analytic solution for a lossless plain coaxial cable, and we do not have to simulate it numerically. But what you possibly would do is, for example, another structure. So we would have an outer conductor, and in it an inner conductor which consists of several disks with different radius. Now this is a low-pass filter, or this structure is used for construction of low-pass filters. Unfortunately, the point is that the field does not change abruptly here, so more or less what you see, what you can measure electrically, like length of the thick part and length of the thin part, is not what you see electrically. The field somehow continues a little bit longer. There is something which is called discontinuity. And the numeric approach to the solution of a coaxial cable mostly handles discontinuities. But the case is that once you have non-ideal coaxial cable, for example, you bent it, you put there a step in the radius of the inner or outer conductor, you put there a change in dielectrics, you mostly invoke all the modes that are possible in that waveguiding structure. But only the dominant one, only the TEM, propagates. The others are evanescent, which means they are attenuating very fast. But what very fast means on the frequency and the dimension, the radius of the coaxial cable and the material inside. So if you have a discontinuity somewhere over here, and now it becomes interesting, the inner conductor would be something like this, rotational symmetric, but anyway, not a plain coaxial cable. Now you need a numeric approach to simulate this. There is no analytic solution for a beast like that. Well, okay, then you have to extend the structure at least to a distance at which all the modes invoked at the discontinuity would be damped sufficiently. That is something you can do analytically, or you can do it in a numeric approach so that you get the coaxial cable, you make the simulation, you get the results, then you make a longer piece of the coaxial cable so that the discontinuity is more distant from the ends, so that the damping, let's say, increases by an order of magnitude. And you make another simulation, and if those are consistent, so you get the same results, then the situation was that you damped sufficiently in both cases, and you can return back for further simulations with the shorter section of the cable. Okay, so we have a cable. We have, for coaxial cables at least, a good boundary condition at the end. Now, how should we find out that properties that are interesting to production or interesting for construction, for example, the dependence of transmission on frequency for such an irregular, possibly manufactured coaxial cable? Well, we would possibly simulate measurement by the numerical experiment. So we will feed some signal in. We will wait for the reflection. And a ratio between input and reflection